Imagine a place where the rules of the cosmos shatter, where distance, that unyielding tyrant, suddenly doesn't exist. For millennia we've stared at the stars, prisoners of light years. But what if there was a cheat code, a hidden passage woven into the very fabric of reality that could take us not just across a galaxy, but through it? You've seen it, haven't you? That impossible swirling vortex, a cosmic throat leading to another star. The film Interstellar burned that image into our collective consciousness. The black hole, Gargantua, and just beyond its terrifying event horizon, a shimmering, hopeful sphere. A gateway. It's a vision so compelling, so audacious, it makes your breath catch. But was it merely Hollywood wizardry? Oh, a beautifully rendered special effect. Or did that film, crafted with scientific rigor, dare to show us a glimpse of humanity's ultimate destiny? Could we one day truly step through such a portal? For generations, the vastness of space has been our greatest challenge, our most profound limitation. We look up at the night sky, and what we see are billions of suns, each a potential home, each a source of wonder. But they are impossibly far away. Think about this. If you could travel at the speed of light, the absolute fastest thing in the universe, the cosmic speed limit, it would still take you over 4 years to reach our nearest stellar neighbor, Proxima Centauri. 4 years just to get to the next star over, to reach the Andromeda Galaxy, our nearest galactic neighbor. It would take you 2.5 million years. You'd need an entire civilization, spanning countless generations, just to make that single journey. It's a crushing reality, isn't it? A universe of infinite possibilities, forever out of reach. This crushing reality has fueled our greatest dreams. The dream of faster-than-light travel, of breaking the cosmic speed limit, of bending space and time to our will. It's a dream born of desperation, a yearning to explore, to discover, to survive. And it's this dream that leads us to one of the most mind-bending, almost mystical concepts in all of physics, the wormhole. Forget what you think you know about straight lines and simple distances. Our universe isn't a flat canvas. It's a dynamic, elastic fabric, space-time, warped and curved by mass and energy. Imagine space-time not as an empty void, but as a giant sheet of paper. If you want to get from one side of the paper to the other, you'd typically draw a line, a long journey across its surface. That's how light travels, how rockets travel. It's the long way around. But what if you could fold that paper? What if you could bring two distant points together, touching? Suddenly, the long journey across the surface becomes a tiny poke through the paper. That tiny poke, that shortcut through the folded fabric of space-time, is what we call a wormhole. Or more formally, an Einstein-Rosen bridge, named after the two brilliant minds who first theorized such a possibility in the 1930s. They discovered that Einstein's own equations of general relativity, the very bedrock of our understanding of gravity and the cosmos, seem to allow for these cosmic shortcuts. An elegant, almost poetic solution to the problem of impossible distances. It sounds too good to be true, doesn't it? A cosmic subway system, a direct express line to another galaxy. And in many ways, it is. The theoretical existence of wormholes is one thing. Their practical, stable existence is another matter entirely. This is where the physics gets a little weird. You see, the wormholes that naturally arise from Einstein's equations aren't exactly the kind you'd want to pilot a spaceship through. They're incredibly unstable. Picture that folded paper again. The moment you try to poke through it, the hole snaps shut. These theoretical natural wormholes would collapse almost instantaneously, faster than light could even cross them. They'd be microscopically small, perhaps no wider than a single atom, and they'd flicker into existence and vanish in a fraction of a second. Not exactly a viable intergalactic highway. So, how do we keep the door open? How do we prevent that cosmic shortcut from slamming shut the moment you try to use it? This is where the concept of exotic matter enters the picture. And it's where science truly starts to feel like science fiction. To stabilize a wormhole, to prop open its mouth and keep it from collapsing under its own immense gravitational pull, you'd need something utterly bizarre. Matter with negative energy density. What does that even mean? Well, every bit of matter we know, you, me, the stars, the planets, it all has positive mass and positive energy. Gravity pulls things together. But exotic matter, if it exists, would do the opposite. It would push things apart. It would create a repulsive gravitational effect. Think of it like a cosmic anti-gravity. Instead of sucking things in, it would push out, holding the wormhole open like an invisible, infinitely strong force field. Finding exotic matter is the holy grail. We've never observed anything like it. Some theoretical models suggest that certain quantum effects might produce tiny amounts of negative energy for fleeting moments, but nothing remotely close to what you'd need to stabilize a macroscopic wormhole. It's like needing a skyscraper built from a handful of dust particles. So, for now, exotic matter remains firmly in the realm of speculation, a hypothetical ingredient in our recipe for faster-than-light travel. But let's be honest, the human spirit isn't easily deterred by the impossible. Our imagination, fueled by films like Interstellar, pushes the boundaries of what we believe can be achieved. It's in our nature to ask, what if? What if we could find exotic matter? What if we could engineer a stable wormhole? Imagine the journey. You approach the mouth of the wormhole, a swirling, shimmering sphere against the backdrop of distant stars. As you draw closer, the space-time around it warps in breathtaking ways, bending the light from distant galaxies into impossible streaks and arcs. It's beautiful, terrifying, and utterly alien. You brace yourself, knowing that beyond this threshold lies a journey unlike any other. You pass through. For a moment, it's a tunnel of pure energy, a kaleidoscope of light and warped space. The forces on your ship would be immense, but our hypothetical exotic matter holds the walls of this cosmic tube stable. You feel a sensation of being stretched, then compressed, as your vessel traverses unimaginable distances in mere moments. And then, as suddenly as it began, you emerge. And what you see, it takes your breath away. The stars are different. The constellations are alien. You're looking at a different galaxy, perhaps one that was millions of light years away, just seconds ago. A new home, a new frontier, a universe of possibilities suddenly within our grasp. It's the ultimate no-wow moment, the culmination of millennia of dreaming. This is the promise of the wormhole, not just faster than light travel, but travel through the fabric of reality itself. It's a concept that challenges our deepest understanding of existence, of distance, and of our place in the cosmos. It tells us that the universe might not be an impenetrable expanse, but a complex tapestry with hidden seams and shortcuts waiting to be discovered. Today, the stable, traversable wormhole remains firmly in the realm of science fiction. We don't have the exotic matter. We don't have the technology. We don't even fully understand the theoretical implications of what such a journey would do to time, to causality, to us. But every great breakthrough, every monumental leap in human understanding began with a dream, with a question, with a wild, impossible, honest what if. The dream of reaching the stars, of truly becoming an interstellar species, is perhaps humanity's greatest aspiration. It's a dream that connects us to every explorer who ever looked beyond the horizon, every scientist who ever peered through a microscope, every artist who ever tried to capture the sublime. We may not have found the key to the wormhole yet, but the fact that we can even imagine it, that our equations allow for it, tells us something profound. It tells us that the universe is far stranger, far more mysterious, and perhaps far more accommodating than we ever dared to believe. The journey to unlock these cosmic secrets has just begun. And the next chapter, well, that takes us to the truly mind-bending possibility. What if these shortcuts don't just bridge space, but also time? Time. It's the ultimate mystery, isn't it? We talk about bending it, skipping through it, even reversing it with theoretical wormholes. But what if we zoom out, way out, beyond any single star, any galaxy, any theoretical shortcut? What if we ask the biggest question of all? Where did time itself begin? Where did space, energy, and everything we know, everything we are, come from? This isn't just about cosmic history. It's about our personal story, etched into the very fabric of existence. Imagine, if you can, a moment not just before things, but before space, before time, before anything we recognize. Modern cosmology, our best scientific understanding, points to an origin point, not an explosion in space, but an explosion of space itself. The Big Bang wasn't a firecracker going off in a pre-existing void. It was the birth of the void, the birth of everything. It's almost impossible to picture, because our brains are hardwired for beginnings within something. But try this. The entire observable universe, all the galaxies, all the stars, every planet, every single atom in your body, was once compressed into a space smaller than the period at the end of this sentence, an unfathomable density, a temperature beyond comprehension. And then, in an instant, too brief to even name, it burst forth. This wasn't just a pop. It was a cosmic roar, a sudden, violent unfurling. In the first fraction of a second, and I mean a fraction of a fraction, like 10 to the power of negative 36 seconds, the universe inflated, growing exponentially, faster than the speed of light itself. Imagine a tiny speck, smaller than a single atom, suddenly ballooning to the size of a grapefruit, and then much, much larger, in less time than it takes light to cross a proton. It wasn't violating any rules, because space itself was expanding, carrying everything along with it. It was like blowing up a balloon, but the balloon itself was the entire universe, and it went from microscopic to cosmic in less than the blink of an eye, smoothing out wrinkles and laying the groundwork for the vast, uniform cosmos we see today. In those first fleeting moments, the universe was a superheated primordial soup. No atoms, no molecules, just a swirling maelstrom of fundamental particles. Quarks, leptons, photons, gluons. It was so hot, so dense, that light couldn't travel freely. The universe was opaque, a blinding fog of pure energy. Think of it like being inside a star, but everywhere all at once. As it expanded, it cooled. And as it cooled, incredible things started to happen. Quarks, which had been zipping around freely, began to bind together, forming protons and neutrons, the building blocks of atomic nuclei. This was the universe's first alchemy, forging the very core of matter. Then came the first 3 minutes. For a brief, precious window, the temperature and density were just right for these protons and neutrons to fuse. Not into heavy elements like carbon or iron. Those would come much, much later, forged in the hearts of stars. But into the simplest elements, hydrogen and helium, 75% hydrogen, 25% helium, a perfect cosmic recipe. Every single hydrogen atom in your body, every helium atom we use to fill balloons, was cooked up in those first 3 minutes. You are, quite literally, made of Big Bang residue. But even after this initial creation, the universe was still too hot for stable atoms. Electrons were still too energetic to settle down with nuclei. So, for the next 380,000 years, the universe remained a thick, ionized plasma, impenetrable to light. This was the cosmic dark ages. No stars, no galaxies, just a vast, expanding sea of neutral hydrogen and helium gas, interspersed with a mysterious, invisible force we call dark matter. Imagine waking up in a universe without light, a universe where nothing shines, just an endless, featureless expanse of cosmic gloom. It sounds bleak, right? But this darkness was pregnant with potential. Those tiny fluctuations, those ripples in the primordial soup, the seeds of future galaxies, were slowly, imperceptibly, being sculpted by gravity. Like an invisible hand, gravity was pulling things together, ever so gently. And then, something extraordinary happened. As the universe continued to cool and expand, it reached a critical temperature. Electrons finally found their homes. They combined with those free-floating protons and helium nuclei to form the first neutral atoms. And in that moment, the universe became transparent. For the very first time, light could travel freely, streaking across the nascent cosmos. That ancient light, that faint afterglow of the Big Bang, is what we detect today as the cosmic microwave background, the CMB. It's not just the oldest light in the universe. It's an actual echo, a fossil radiation from a time when the universe was only 380,000 years old, a mere infant in its 13.8 billion year journey. When you tune an old analog TV to an empty channel and see that static, about 1% of it is actually noise from the Big Bang itself. It's the universe's first baby picture, a direct message from the dawn of time, and it tells us volumes about its earliest moments, confirming our cosmic origin story with incredible precision. But even with light finally free, the universe was still overwhelmingly dark. Billions of years had to pass before anything truly spectacular happened. Those tiny gravitational clumps, formed during the Dark Ages, grew larger and larger. Hydrogen and helium gas began to collapse under their own immense weight. The pressure and temperature at their cores rose, higher and higher, until ignition. Suddenly, across the vast, empty expanse of the cosmos, the first stars flickered to life. Massive, brilliant, hydrogen-burning behemoths. These were the universe's primordial lighthouses, piercing the cosmic gloom, ending the Dark Ages forever. They were fierce, short-lived titans, burning through their fuel at an astonishing rate. And within their fiery hearts, something truly revolutionary occurred. These first stars were the universe's original alchemists. For the first time, hydrogen and helium were fused into the first heavy elements: carbon, oxygen, nitrogen, iron, the very ingredients necessary for rocky planets, for liquid water, for amino acids, for life, for ethitbato. Imagine before this, the universe was barren, chemically simple. These stars were the factories, the foundries, creating the raw materials for everything that would follow. When these colossal stars eventually exploded in spectacular supernovae, cataclysms of unimaginable power, they scattered these newly forged elements across the cosmos, enriching the interstellar medium, seeding the next generation of stars and the generation after that. Every time you breathe, you're inhaling oxygen born in a star. Every time your heart beats, iron forged in a stellar furnace is at work. You are literally, profoundly stardust. From ancient campfire stories about cosmic eggs and divine creators to complex mathematical equations and multi-billion-dollar telescopes, humanity has always wrestled with the same fundamental questions. Where did we come from? How did all this begin? Our myths tried to explain it, painting vivid pictures of Genesis. Our science, equally driven by wonder, seeks to uncover the precise mechanisms. Today, instruments like the James Webb Space Telescope are literal time machines. They don't just look out into space, they look back in time. Because light takes time to travel, when Webb gazes at the most distant galaxies, it's seeing them as they were billions of years ago, capturing the faint glow of those very first stars, the echoes of creation itself. It's like looking at an ancient family album, tracing our lineage back to the very first light. And what we find in that album is astounding. We find a universe that started from almost nothing, from a point of unimaginable density and heat, and expanded into the vast, intricate tapestry we see today. We find that the atoms in our bodies, the carbon in our bones, the oxygen in our breath, the iron in our blood, were forged in the hearts of long-dead stars, scattered across the cosmos, and eventually gathered into our solar system, into our planet, into you. Think about the sheer audacity of this journey. From a speck smaller than an atom, to a universe stretching billions of light years across. From a blinding opaque plasma, to a cosmos filled with glittering galaxies. From simple hydrogen and helium, to the incredible complexity of life, consciousness, and societies capable of contemplating their own origins. If the entire history of the universe, 13.8 billion years, were compressed into a single calendar year, the Big Bang happens on January 1st. Those first stars ignite in late January. Our solar system and Earth don't even form until early September. Dinosaurs appear in mid-December. And all of human history, from the first hominids to the invention of the Internet, is confined to the very last minutes of December 31st. We are truly latecomers to this cosmic party. But being latecomers doesn't diminish our significance. It amplifies it. We are the universe observing itself. We are the consciousness that emerged from stardust, capable of looking back across unimaginable gulfs of time and space, piecing together the story of everything. We are the legacy of those first stars, the direct descendants of the Big Bang itself. This isn't just science, it's poetry. It's a profound connection to something infinitely larger than ourselves. It tells us that our existence isn't just happenstance. It's a continuation of the universe's grand, unfolding narrative. Every atom in your hand whispers the story of a cosmic birth, of a dark age overcome, of stars igniting and scattering their gifts. You are, in every sense, a child of the cosmos. But the story doesn't end with the first stars. Oh no. Those pioneering beacons of light were just the beginning. The universe had so much more to create. They paved the way for galaxies, for planets, for all the breathtaking complexity that would follow. And as we gaze at their ancient light, we're left with a burning question. What happened next? How did a universe of gas and dust transform into the intricate cosmic web we inhabit today? And what incredible forces were at play, shaping the very destiny of our universe, long before we even existed? And so we asked, what happened next? How did a universe of seemingly simple gas and dust transform into the intricate cosmic web we inhabit today? And what incredible forces were at play, shaping the very destiny of our universe, long before we even existed? Well, the answer, like so much in the cosmos, is both incredibly complex and beautifully elegant. It all comes down to the universe's most patient, relentless sculptor, gravity. Imagine the early universe, just a few 100 million years after the Big Bang. It's not quite a uniform soup. There are tiny, imperceptible lumps, regions where the hydrogen and helium atoms, along with the mysterious, invisible dark matter, are ever so slightly denser. These aren't dramatic differences. We're talking about fractions of a percentage. But in the colossal arena of the cosmos, those tiny variations were everything. They were the seeds. Gravity, that quiet, persistent force, began its work. It didn't rush. It couldn't. It just pulled. Over eons, those denser regions, ever so slowly, attracted more and more matter, like an invisible hand gathering dust motes into ever larger clumps. Gravity began to sculpt the nascent universe. Billions of years passed. That's not a typo. Billions? The universe had time on its side, an almost infinite canvas upon which to paint its masterpiece. As these colossal clouds of gas and dark matter grew, they started to collapse in on themselves, spinning faster and faster due to the conservation of angular momentum, the same physics that makes a figure skater spin faster when they pull their arms in. These weren't yet the majestic spiral or elliptical galaxies we see today. These were proto-galaxies, primal swirls of gas, like cosmic eddies forming in a vast dark ocean. They were the nurseries, the cradles where the second generation of stars and all subsequent generations would ignite. You see those first stars, the population 3 giants we talked about. They burned bright and died fast, enriching their immediate surroundings with the very first heavy elements. But it was within these growing, spinning proto-galaxies that a grander ballet began. Gravity continued to pull, compressing the gas, heating it up, until countless new stellar furnaces roared to life. This was the true dawn of galactic formation, a magnificent, slow-motion explosion of light across the universe. And what a sight it must have been. Not a single uniform burst, but a symphony of countless individual star births, each one a tiny act of creation within a larger evolving whole. These early galaxies were often chaotic, clumpy, and vibrant, their light stretching across unimaginable cosmic distances, already hinting at the breathtaking diversity that would emerge. But galaxies aren't just static islands of stars. Oh no. They're dynamic, living entities, constantly interacting, pulling at each other with their immense gravitational fields. Imagine 2 colossal stellar cities, each containing hundreds of billions of suns, on a collision course. Sounds terrifying, right? Like the ultimate cosmic catastrophe. But in the vast, empty expanse of space, galactic collisions are rarely the destructive events we might imagine. Think about it. The stars themselves are incredibly far apart, even within a galaxy. If our sun were a grain of sand, the nearest star, Proxima Centauri, would be another grain of sand over 10 miles away. So when galaxies merge, individual stars rarely collide. Instead, it's like 2 clouds of stardust passing through each other. Gravity, though, is the ultimate matchmaker. It warps, it stretches, it reshapes. Galactic mergers are slow, graceful dances that can last for hundreds of millions of years, often triggering incredible bursts of new star formation as gas clouds are compressed. Our own Milky Way galaxy, that familiar band of light across our night sky, is itself the product of countless such mergers. And it's still happening. Right now, as you listen to my voice, the Andromeda Galaxy, our majestic nearest galactic neighbor, is hurtling towards us at about 250,000 miles per hour. In about 4.5 billion years, our 2 colossal galaxies will begin their slow, elegant collision. The result won't be destruction, but a new, larger, more elliptical galaxy that astronomers have already dubbed Milkomeda. It's a cosmic embrace, a grand act of creation on the largest scales. And these galaxies, these swirling islands of stars, they aren't just floating randomly in the void. They're connected. Look up at the night sky, and you might see individual stars, maybe even a hazy galaxy. But zoom out, far beyond the reach of any telescope, and you'd see something truly mind-bending. The cosmic web. Imagine the universe as a colossal three-dimensional spiderweb. Galaxies aren't uniformly distributed. They're clustered along vast luminous filaments of gas and dark matter, separated by immense empty voids. These filaments intersect at giant nodes, where massive galaxy clusters containing thousands of galaxies reside. It's like the universe organized itself into a gigantic interconnected neural network, with the galaxies as the glowing synapses. This isn't a random pattern. It's the direct result of gravity, working patiently over billions of years, pulling matter towards those initial, tiny density fluctuations, shaping the largest structures in the universe. But let's zoom back to the heart of these galaxies, to the stars themselves. Because those stars aren't just points of light, they are the universe's alchemists. They are the cosmic forges, tirelessly working to create something far more complex than just hydrogen and helium. This is where the story of stardust truly comes alive. Remember, the very first stars were made almost entirely of hydrogen and helium. They fused these light elements into slightly heavier ones, like carbon and oxygen. But it was the next generations of stars, born in the enriched gas clouds of newly forming galaxies, that really began to work their magic. Our Sun, for instance, is a second or third generation star. It's not just burning hydrogen, it's burning a mix of elements that were forged in the hearts of stars that lived and died before it. Think about that for a moment. The material that makes up our Sun, our Earth, and indeed you, has been processed and reprocessed through countless stellar lives and deaths. Inside the cores of massive stars, temperatures and pressures reach unimaginable extremes. Here, the process of stellar nucleosynthesis kicks into high gear. Hydrogen fuses into helium. Helium fuses into carbon. Carbon fuses into oxygen. Then neon, magnesium, silicon, and all the way up the periodic table, element by element, until you reach iron. Iron is the cosmic dead end for stellar fusion, because fusing iron actually consumes energy rather than releasing it. And that's where the drama truly begins. When a massive star runs out of fuel to fuse in its core and starts producing iron, it can no longer support itself against the crushing force of its own gravity. The core collapses in an instant, triggering one of the most spectacular events in the universe, a supernova. And it's in that glorious cataclysmic explosion that the universe completes its grand alchemy. The intense shock waves and unimaginable energy of a supernova are powerful enough to fuse elements heavier than iron, elements like gold, silver, uranium. Imagine that. The very gold in your jewelry, the iron in your blood, the calcium in your bones. Every single one of those atoms was forged in the heart of an ancient star, or in the fiery explosion of a supernova billions of years ago. This isn't a metaphor. This is science. This is the profound, undeniable truth of our existence. We are quite literally stardust. Every atom that makes up your body has a cosmic origin story, a journey through the heart of stars, across vast interstellar distances, before finally coalescing into the planet Earth, and eventually into you. Astronomers, with their telescopes and their tireless curiosity, were the first to truly glimpse this grand connection. From the early 20th century, brilliant minds like Cecilia Payne-Gaposchkin dared to look at the light from distant stars and realize that their spectra revealed their true composition, mostly hydrogen and helium. Later, scientists like Fred Hoyle and Margaret Burbidge pieced together the incredible puzzle of how stars forge heavier elements. Their work, their insights, weren't just about cataloging data. They were about uncovering the fundamental truth of our place in the universe, inspiring generations with the knowledge that we are intimately connected to the cosmos. So when you look up at the night sky, You're not just seeing distant pinpricks of light. You're seeing the very architects of your existence. You're seeing the grand, ongoing saga of galactic formation, the relentless work of gravity, and the magnificent alchemy of stars. You're seeing a universe that, from its humble beginnings, has been tirelessly building, evolving, and creating, culminating in the very existence of conscious beings like us, capable of looking back and understanding its story. This isn't just a story of physics, it's a story of profound belonging. It tells us that we are not outsiders looking in, but integral participants in the universe's grand unfolding narrative. Every breath you take, every thought you think, is a testament to billions of years of cosmic evolution. But the universe's creative work didn't stop with the formation of galaxies and the forging of elements. Oh no. From this cosmic dust, from these scattered gifts of dying stars, something even more intricate and beautiful would begin to emerge. Something that would set the stage for possibilities beyond our wildest dreams. Because from this stardust, from these swirling galactic nurseries, the universe was preparing to craft something truly extraordinary. The very worlds upon which life itself might one day flourish. And that is where our next cosmic journey begins. And that is where our next cosmic journey begins. Imagine for a moment soaring through the inky black, past dazzling nebulae and ancient star clusters, until a familiar shape begins to resolve itself in the distance. A grand, swirling pinwheel of light, stretching 100,000 light-years across, home to hundreds of billions of stars. This, my friends, is our address in the universe. This is the Milky Way. We often picture ourselves as floating alone in the cosmos, but we're not. We are nestled within one of the Milky Way's majestic spiral arms, the Orion Arm, a vibrant, bustling cosmic neighborhood. Our galaxy, this is a breathtaking, dynamic city of stars, constantly spinning, evolving, and giving birth to new worlds. It's been doing this for over 13 billion years. A dance of gravity and light that has sculpted the very fabric of our existence. But how did our particular corner of this cosmic metropolis come to be? How did we get our star, our planets, our home? Well, it all started with a whisper, a subtle ripple in a vast cloud of gas and dust. For eons, this particular cloud, many light years wide, had drifted through space, largely unremarkable. But then, perhaps a passing supernova, a shockwave from a distant star's death, provided the trigger. A tiny region within that cloud began to clump ever so slightly, a little denser than its surroundings. And in the vacuum of space, even a tiny difference in density can become a cosmic destiny. Gravity, that relentless sculptor of the universe, took hold. Slowly, inexorably, the cloud began to collapse in on itself. Think of it like a cosmic drain, drawing in material from all directions. As it collapsed, it spun faster and faster, flattening into a vast, rotating disk. A stellar nursery, pregnant with the promise of a star. At the very center of this swirling maelstrom, the pressure and temperature began to skyrocket. Hydrogen atoms, the most abundant element in the universe, were squeezed closer and closer together, faster and faster, until the unimaginable happened. They fused. Two hydrogen nuclei slammed together to form helium, releasing an explosive burst of energy. Ignition. Our sun was born, and with its birth, a new era dawned. For millions of years, this newborn star raged, a fiery inferno in the cosmic dark. But it wasn't alone. Surrounding it, still caught in that swirling disk of gas and dust, were the leftovers, the cosmic debris that hadn't been swallowed by the infant sun. This was the raw material, the building blocks, for everything else in our solar system. Imagine billions of tiny particles, grains of cosmic sand and ice, rubbing shoulders in this primordial disk. Over vast stretches of time, they began to stick. Electrostatic forces, like static cling, pulled them together. Dust bunnies grew into pebbles. Pebbles coalesced into rocks. Rocks smashed into each other, sometimes shattering, sometimes merging, slowly forming larger and larger bodies. The planetesimals, it was a chaotic, violent time. A cosmic demolition derby happening on an unimaginable scale. For millions of years, these infant worlds battled it out, gravitationally clearing their orbits, either sweeping up the debris or ejecting it into the cold depths of space. And as they did, a pattern began to emerge. Close to the blazing sun, where temperatures were scorching, only hardy materials like rock and metal could survive. These would become the inner rocky planets: Mercury, Venus, Earth, and Mars. Further out, beyond what scientists call the Nipauner snow line, where it was cold enough for ice to condense, the story changed. Here, the planetesimals could gather not only rock, but also vast quantities of frozen water, methane, and ammonia. These became the cores of the gas giants: Jupiter, Saturn, Uranus, and Neptune. Monstrous worlds that then gravitationally hoovered up. Vast envelopes of hydrogen and helium gas, growing to sizes that dwarf our little Earth. And speaking of Earth, let's talk about our home, our blue marble. It formed from the very same cosmic dust as its siblings, a fiery ball of molten rock, constantly bombarded by asteroids and comets, a hellscape utterly inhospitable to life. But then, something truly extraordinary happened. A colossal impact. Picture a Mars-sized object, dubbed Theia, slamming into the young Earth. The collision was catastrophic, ripping away a huge chunk of our planet, sending molten debris hurtling into orbit. And from that debris, our moon was born. This wasn't just a pretty companion in the night sky. The moon was a cosmic gift. Its gravitational pull stabilized Earth's axial tilt, preventing our planet from wobbling wildly like a top, which would have led to extreme chaotic climate shifts. It also created the tides, rhythmic pulses that may have been crucial in the very first stirrings of life in ancient oceans. Without that impact, without our moon, Earth might have remained a barren, lifeless rock. But the moon wasn't the only serendipitous factor. Our location in the solar system is utterly crucial. We reside in what astronomers affectionately call the Goldilocks zone. Not too hot, not too cold, but just right. We're far enough from the sun that water can exist as a liquid, but close enough that it doesn't freeze solid. Liquid water, that humble, miraculous molecule, is the solvent of life. It allows chemical reactions to occur, transports nutrients, and regulates temperature. No liquid water, no life as we know it. For billions of years, Earth slowly cooled. Volcanic outgassing formed our early atmosphere. Comets, these icy wanderers from the outer solar system, may have delivered vast quantities of water, filling our oceans. And in those ancient seas, something truly astounding began. Simple organic molecules, born from lightning strikes and hydrothermal vents, started to self-assemble. The precise mechanisms are still a profound mystery, a puzzle scientists are passionately trying to solve. But the result is undeniable. Life emerged, from single-celled organisms to the first photosynthesizers that slowly, painstakingly, began to pump oxygen into our atmosphere. A process so transformative, it's called the Great Oxidation Event. To the Cambrian explosion of complex life, our planet has been a vibrant, dynamic laboratory of evolution. Every single living thing you see, from the towering redwood to the smallest bacterium, is a direct descendant of those pioneering cells that first sparked into being billions of years ago. We are all connected, not just to each other, but to every organism that has ever called this planet home. For most of human history, we gazed up at the night sky with wonder, fear, and a profound sense of ignorance. The stars were pinpricks of light, perhaps holes in a celestial sphere, or gods watching over us. Our Earth, we believed, was the unmoving center of creation. Then, a quiet revolution began. A Polish astronomer named Nicholas Copernicus dared to suggest something radical. Maybe the Earth wasn't the center. Maybe we revolved around the sun. It was a dangerous idea, one that challenged millennia of deeply held beliefs, and it took immense courage, even defiance, for those who followed him to champion it. Galileo Galilei, with his crude telescope, turned the lens to the heavens and saw moons orbiting Jupiter. Undeniable proof that not everything revolved around Earth. Johannes Kepler painstakingly mapped planetary orbits, revealing their elliptical paths. Isaac Newton, with his universal law of gravitation, finally explained why the planets moved the way they did, unifying the celestial and terrestrial under a single elegant principle. These weren't just scientific breakthroughs. They were philosophical earthquakes, each one chipping away at our cosmic egocentricity, humbling us, yet also empowering us with knowledge. Fast forward to our modern era, and our understanding has exploded. Powerful telescopes, both on Earth and in space, like the Hubble and the James Webb, have given us unprecedented views of our solar system and beyond. We've sent robotic emissaries to almost every planet, rovers crawling across Mars, probes dipping into Jupiter's atmosphere, orbiters mapping the icy moons of Saturn. The Voyager probes, launched in the 1970s, have traveled beyond the heliosphere into interstellar space, carrying a golden record, a message in a bottle for any intelligence they might encounter. But perhaps the most profound moment in our understanding of Earth came not from a new discovery, but from a simple photograph. In 1990, Voyager 1, 6 billion kilometers from home, turned its camera back towards Earth. The resulting image, famously dubbed the Pale Blue Dot U by Carl Sagan, showed our entire world as a tiny, almost imperceptible speck of light, suspended in a sunbeam. Everything we know, everyone we've ever loved, every war, every triumph, every sorrow, existed on that single fragile mote of dust. It was a stark, humbling reminder of our place in the universe. And it's a reminder of Earth's preciousness. Our planet, this vibrant oasis in the void, is incredibly rare. We've found thousands of exoplanets, but none yet that are a true twin to Earth, teeming with complex life. This blue marble, with its liquid water, its protective atmosphere, its stable climate, and its incredible biodiversity, is a miracle. It's a testament to billions of years of cosmic serendipity, a delicate balance of conditions that allowed life to not just survive, but to flourish. This isn't just our home. It's the only home we've ever known. It's a gift, a profound inheritance from the universe itself, and understanding its journey from swirling cosmic dust to the vibrant, living world we inhabit today fills us with a quiet gratitude. What an intimate connection to the forces that shaped us. It grounds us, reminding us that while we reach for the stars, our roots are firmly planted in this extraordinary soil. But as we look out into the vastness, as we grapple with the incredible journey of our home planet, a fundamental question lingers. If Earth is so unique, so special, so miraculously suited for life, does that mean we are alone? Or, out there, beyond the familiar warmth of our sun, beyond the reach of our current telescopes, are there other pale blue dots, other oases, waiting to be discovered? And if so, how do we find them? What incredible stories might they have to tell? The search, the most profound quest humanity has ever undertaken, has only just begun. But as we look out into the vastness, as we grapple with the incredible journey of our home planet, a fundamental question lingers. If Earth is so unique, so special, so miraculously suited for life, Does that mean we are alone? Or out there, beyond the familiar warmth of our sun, beyond the reach of our current telescopes, are there other pale blue dots, other oases, waiting to be discovered? And if so, how do we find them? What incredible stories might they have to tell? The search, the most profound quest humanity has ever undertaken, has only just begun. For centuries, millennia even, humanity looked up at the night sky and saw only pinpricks of light. Our own solar system, with its handful of wandering stars, its familiar planets, was the entire universe to us. We knew Jupiter, a grand swirling marble, and Saturn, crowned with its impossible rings. We knew Mars, a rusty echo of Earth, and Venus, shrouded in poisonous clouds. But even in our own cosmic backyard, the diversity, the sheer variety of worlds is breathtakingly profound, a testament to the myriad ways a planet can be forged. Think about it. We have Earth, a miracle of liquid water and temperate air. But just a little further out, a colossal shift in cosmic architecture takes hold. You hit Jupiter, a world so vast, you could fit over 1,000 Earths inside it. It's a gas giant, a swirling maelstrom of hydrogen and helium, a planet that never quite made it to star status. Its colossal great red spot, a storm larger than our entire planet, has raged for centuries. And then there are its moons. Io, a volcanic hellscape, constantly resurfaced by tidal forces from Jupiter's immense gravity. A world where lava lakes glow like angry eyes in the perpetual twilight. Or Europa, a smooth, cracked sphere of ice, hiding beneath its frozen shell, what scientists believe is a vast, salty ocean. An ocean that could hold more water than all of Earth's oceans combined. An ocean warmed by Jupiter's gravitational squeeze, potentially a cradle for life. And then Saturn. Oh, Saturn. Those rings, a symphony of ice and rock, each particle a tiny moonlet, orbiting in perfect, impossible harmony. If you could fly through them, you wouldn't see solid bands. You'd see 1 trillion individual pieces, from dust motes to mountain-sized chunks, all dancing in an intricate ballet. And Saturn, too, has its secrets. Titan, its largest moon, a world so strange it feels ripped from a sci-fi novel. It's shrouded in a thick orange atmosphere, denser than Earth's, where methane rain falls and rivers of liquid methane carve channels into an icy landscape. It has lakes, seas, even clouds. A world with its own hydrological cycle, just fueled by a different liquid. Further still, the ice giants, Uranus and Neptune, distant, mysterious, cloaked in deep blue and turquoise hues, battered by supersonic winds. These worlds are still largely unknown, their secrets whispered across billions of miles of empty space. And beyond them, the Kuiper Belt, a vast cosmic junkyard of icy bodies, home to dwarf planets like Pluto, once a proud planet, now a reclassified king of its own frigid domain. All these worlds, born from the same swirling disk of gas and dust around our infant sun. All of them, celestial architects, building themselves into wildly different forms, depending on their distance from the star, the available building materials, and the colossal cosmic forces that shaped them. Our solar system, it turns out, is a dazzling, diverse collection, a cosmic sampler pack of planetary possibilities. And for a long time, we thought this was it. Our cosmic neighborhood, our little corner of the universe. But then, everything changed. For centuries, the idea of planets orbiting other stars was pure science fiction, a delightful thought experiment for philosophers and dreamers. The universe felt vast, yes, but also intimately familiar. We knew the sun, the moon, the planets we could see. That was our celestial stage. But in the early 1990s, the dream began to solidify. Scientists, driven by an insatiable curiosity and armed with increasingly sophisticated instruments, started to look for the faint, telltale signs of other worlds. It was like trying to spot a firefly against the glare of a distant lighthouse, but they persisted. And then, the breakthrough. In 1995, Swiss astronomers Michel Mayor and Didier Queloz announced the discovery of 51 Pegasi b, the first confirmed exoplanet orbiting a sun-like star. The universe suddenly exploded with possibilities. It wasn't just our sun that had planets. It wasn't just our solar system that was special. It was a cosmic revelation, a moment when humanity collectively realized that the universe was far, far grander than we had ever dared to imagine. Think about this for a second. Our Milky Way galaxy alone contains hundreds of billions of stars, and observations tell us that most of those stars, perhaps all of them, have planets orbiting them. So if we're talking hundreds of billions of stars, and each has, on average, at least one planet, well, you do the math. We're talking about trillions of planets in our galaxy alone. And our galaxy is just one of billions of galaxies. It's an almost incomprehensible number, a cosmic lottery with tickets for every imaginable world. If you ever felt small before, this fact tends to rearrange your perspective. So, how do you find a planet that's light years away, often dwarfed by the blinding brilliance of its parent star? It's not like you can just point a telescope and see it. Most exoplanets are far too small and too dim to be directly imaged, at least with our current technology. It's like trying to see a mosquito buzzing around a distant floodlight. Instead, scientists have become cosmic detectives, looking for indirect clues, for the subtle whispers that betray a planet's presence. One of the most powerful techniques is called the radial velocity method, or the wobble method. Imagine a giant parent swinging a tiny child around. The child is orbiting the parent, right? But the parent also wobbles a little, ever so slightly in a tiny circle. That's because the child's gravity tugs on the parent too. It's the same with a star and its planet. The planet's gravity pulls on its star, causing the star to wobble back and forth ever so slightly. We can't see the wobble directly, but we can measure the star's light. As the star wobbles towards us, its light shifts slightly to the blue end of the spectrum, what we call blue shift. As it wobbles away, its light shifts to the red end, red shift. By meticulously measuring these tiny shifts, scientists can deduce not only that a planet is there, but also its mass and how close it orbits its star. It's an incredible feat of precision, like listening to a whisper from across a continent. But the real game changer, the method that has unveiled the vast majority of known exoplanets, is the transit method. This one is a bit like watching a tiny fly crawl across a distant light bulb. If a planet's orbit happens to be perfectly aligned with our line of sight, it will occasionally pass directly in front of its star. When it does, it blocks a tiny fraction of the star's light, causing a momentary minuscule dip in the star's brightness. It's an almost imperceptible flicker, sometimes as small as 1/100%. But our telescopes are so sensitive now, they can catch it. By observing these repeated dips, scientists can confirm the presence of a planet, determine its size, and even calculate how long its year is. It's how missions like the Kepler Space Telescope, a dedicated planet-hunting observatory, revolutionized our understanding of exoplanets, discovering thousands of new worlds and proving that planets are not just common, they are ubiquitous. What we've found out there is both astounding and humbling. The exoplanet zoo is far more diverse than our own solar system. We've found hot Jupiters, colossal gas giants orbiting so close to their stars that their atmospheres are literally boiling away. We've found super-Earths, rocky worlds larger than Earth but smaller than Neptune, a type of planet we don't even have in our own neighborhood. We've found mini-Neptunes, and even planets orbiting two stars. Like Luke Skywalker's Tatooine, some planets are rogue, cast out from their parent stars, drifting alone through the cold, dark, interstellar void. This incredible diversity tells us that the universe is a far more creative architect than we ever imagined. Planets aren't just forming in one specific way. They're forming in every conceivable permutation, under every conceivable condition. And among this staggering variety, the perennial question rings louder than ever. Are we alone? The search for life beyond Earth, once relegated to the realm of fiction, is now squarely in the domain of serious science, and we're pushing the boundaries of what's possible. The James Webb Space Telescope, humanity's most powerful eye on the cosmos, isn't just looking for planets. It's looking at them. It's designed to analyze the light from distant stars that has passed through the atmospheres of their orbiting planets. By doing so, it can detect the chemical fingerprints of gases like oxygen, methane, or even water vapor. Potential biosignatures, signs that hint at the presence of life. Imagine for a moment the thrill. Imagine pointing Webb at a distant super-Earth, billions of miles away, and detecting oxygen, real, undeniable oxygen. It would be a moment that would rewrite every textbook, every philosophy, every aspect of what it means to be human. It would be the most profound discovery in the history of our species. We are just beginning this incredible journey. Each new exoplanet discovered, each faint wobble, each tiny dip in starlight, is a step closer to answering that fundamental question. We're no longer just looking at points of light. We're seeing entire worlds, entire solar systems, emerging from the cosmic dust, each with its own story, its own potential for life. The universe, it turns out, is a canvas of endless creation, a symphony of worlds, and somewhere out there, among those trillions of possibilities, is a story waiting to be told. A story that might just include us. But to truly listen, to truly hear the universe's answer, we need to understand how life itself began, and where it might be hiding. But to truly listen, to truly hear the universe's answer, we need to understand how life itself began, and where it might be hiding. But before we can truly imagine what it means to find life out there, before we can even begin to dream of reaching those distant shores, we have to confront the ultimate cosmic architects, the universe's most enigmatic monsters. We have to reckon with the very fabric of reality itself and the terrifying, beautiful voids that tear it apart. This is where the interstellar dream begins to truly intersect with reality, where the science of space-time gets utterly, breathtakingly weird. Because to understand the deepest secrets of the cosmos, we must first dare to stare into the abyss. We must talk about black holes. For centuries, they were just theoretical whispers, mathematical curiosities born from the mind of Albert Einstein. But today, they are as real as the stars themselves. Black holes aren't just empty space. They're not cosmic vacuum cleaners, sucking up everything in their path. No, they are the universe's ultimate gravitational prisons, places where gravity has won, utterly and completely. Imagine a star, much more massive than our sun, living out its long, brilliant life. It fuses hydrogen into helium, then helium into carbon, and so on, until its core is a dense iron heart. But iron doesn't fuse. It can't create enough outward pressure to fight the crushing force of its own gravity. And that's when it happens. The star runs out of fuel. The outward push from fusion stops. There's nothing left to resist the immense inward pull. In a fraction of a second, the star collapses in on itself, an implosion so violent, so catastrophic, it triggers one of the most spectacular events in the cosmos, a supernova. For a fleeting moment, it outshines an entire galaxy, a cosmic death rattle echoing across unimaginable distances. But what remains? If the star's core is dense enough, if its mass is above a certain threshold, the collapse doesn't stop. It doesn't just become a neutron star, an atomic nucleus the size of a city. No, it keeps going. It collapses past the point of matter as we know it. It compresses into an infinitely small, infinitely dense point, a singularity. And around this singularity, gravity becomes so intense, so overwhelming, that nothing, not even light itself, can escape its grasp. This is the event horizon. It's not a physical surface you can touch, like the surface of a planet. Think of it as the ultimate cosmic boundary, a one-way door to nowhere. Once you cross it, you're committed. There's no turning back. No matter how powerful your rockets, no matter how fast you fly, the universe outside simply recedes into an impossible distance. You are traveling inevitably towards the singularity and towards your own ultimate agonizing end. It's like being caught in a river that's flowing faster than you can swim. Once the current exceeds your maximum speed, you're going over the waterfall. The event horizon now is that point of no return. Now, to truly grasp the mind-bending reality of black holes, we have to talk about space-time. Einstein taught us that space and time aren't separate, rigid entities. They are interwoven, a single flexible fabric that permeates the entire universe. Think of it like a giant trampoline or a stretched rubber sheet. If you place a bowling ball in the middle, it creates a dip, a curve in the fabric. That curve, that distortion, is what we experience as gravity. The Earth, a smaller marble, doesn't fall into the bowling ball because of some invisible force pulling it directly. Instead, it rolls around the curve, perpetually falling, but never quite reaching the center. That, in essence, is how planets orbit stars. They're just following the curves in space-time created by massive objects. Now imagine a black hole. It's not just a bowling ball. It's a literal punch through the fabric of space-time. A tear. The curvature it creates is so profound, so steep, that once you get close enough, there's no way to roll out. Everything, including light, simply slides down into the abyss. It's the ultimate cosmic drain. This extreme warping of space-time has profound, almost unimaginable consequences. One of the most famous, and perhaps unsettling, is time dilation. In the presence of immense gravity, time itself slows down. This isn't science fiction. It's a proven fact. GPS satellites orbiting Earth have to account for tiny relativistic effects on their clocks. But near a black hole, the effects are staggering. Remember Matthew McConaughey's character, Cooper, in Interstellar? He visits Miller's planet, orbiting the supermassive black hole Gargantua. For every hour he spends on that planet, 7 years pass back on Earth. That's not just a plot device. That's a direct, albeit extreme, application of Einstein's general relativity. The gravity well of Gargantua is so intense that time for Cooper slows to a crawl compared to his children back home. It's a heartbreaking illustration of how black holes don't just bend light, they bend our very experience of existence. And what about you? If you were to cross that event horizon, it wouldn't be a quick, clean end. As you fell deeper into the black hole's grip, the gravitational pull on your feet would be exponentially stronger than the pull on your head. Your body would be stretched and elongated, like a piece of spaghetti, until you were ripped apart atom by atom. Scientists even have a delightfully gruesome name for it: spaghettification. It's a truly horrific way to go, but a testament to the sheer unbridled power of these cosmic leviathans. For a long time, black holes were considered exotic rarities, the remnants of a few exceptionally massive stars. But we now know they are everywhere. We've detected stellar mass black holes, born from the death of individual stars, lurking in binary systems, slowly devouring their companion stars. We've even imaged their event horizons, thanks to incredible collaborations like the Event Horizon Telescope, giving us the first direct glimpse of these cosmic beasts. The fuzzy orange donut you've seen? That's not the black hole itself, but the superheated plasma swirling around its edge, just before it plunges into oblivion. But the real monsters of the cosmos are the supermassive black holes. These aren't just a few times the mass of our sun. They're millions, even billions, of times more massive. And almost every large galaxy, including our own Milky Way, harbors one, and at its very heart, our own supermassive black hole, Sagittarius A, is 4 million times the mass of the sun. And it sits silently, majestically, at the center of our galaxy, a gravitational anchor around which hundreds of billions of stars gracefully orbit. These galactic behemoths aren't just passive observers. They play a crucial role in the evolution of galaxies. Their immense gravity influences the formation of stars, the movement of gas clouds, and even the overall shape of the galaxy itself. They are the quiet, colossal conductors of the cosmic symphony, orchestrating the dance of stars across unimaginable scale. The existence of black holes, their fundamental nature, and their profound impact on space-time force us to confront the very limits of our understanding. They are the ultimate cosmic laboratories, places where the laws of physics as we know them break down. Inside the event horizon, inside that singularity, our equations fail. General relativity, which describes gravity on the grandest scales, clashes violently with quantum mechanics, which describes the universe on the smallest scales. We don't have a unified theory that can explain what happens at the heart of a black hole. And that's one of the biggest mysteries in modern physics. Could there be something beyond the singularity? Could black holes be gateways to other universes, other dimensions? The science fiction writer in all of us screams yes, but the physicist in us, the one grounded in evidence, is much more cautious. The idea of wormholes, or Einstein-Rosen bridges, those theoretical tunnels through space-time that Interstellar famously depicted, is a fascinating one. It proposes a shortcut, a way to traverse unimaginable cosmic distances in an instant, by bending space-time back on itself. But are they real? Could they exist? And if they do, could we ever hope to traverse one, to step through a cosmic doorway and emerge in a distant galaxy, or even a different time? We've barely scratched the surface of understanding the black holes we can observe, let alone the theoretical concepts that push the boundaries of reality itself. What we do know is this: black holes are not just theoretical constructs. They are fundamental, powerful components of our universe, shaping galaxies, bending time, and challenging our deepest assumptions about reality. They are terrifying and beautiful, destructive and creative, and they stand as a monumental testament to the universe's capacity for the utterly bizarre. They are the ultimate frontier, the ultimate mystery, and perhaps the ultimate key to understanding what lies beyond. Because if we truly want to journey to those distant exoplanets, if we truly want to understand the universe's grand design, we first have to understand the extreme physics that govern it. We have to understand what happens when gravity becomes absolute, and what happens when the fabric of space-time itself is twisted, torn, and folded. What happens then, when we consider what kind of journey it would take to actually get to those distant worlds? Could we ever truly bridge the unimaginable cosmic distances that separate us from other life, other civilizations? Or are we forever confined to our own cosmic neighborhood, gazing across an ocean of space-time we can never hope to cross? It's a question that brings us face to face with the most ambitious dream humanity has ever dared to conceive. It's a question that brings us face to face with the most ambitious dream humanity has ever dared to conceive. Remember that moment, Cooper, hurtling towards the abyss, defying everything we know about black holes, because he had to. He had to go beyond. And he did. He passed through not just a black hole, but a wormhole. A cosmic shortcut placed there seemingly by some unseen entity. It was one of the most visually stunning, scientifically plausible, yet utterly mind-bending sequences ever put on film. But was it just Hollywood magic? Or does humanity truly, deeply harbor the hope that one day we might actually step through a gateway like that? Could we, too, find a way to bridge the unimaginable gulfs of space-time, to reach other stars, other worlds, in the blink of an eye? The idea itself is intoxicating. Imagine 2 points in space, light years apart, so far, in fact, that even a journey at the speed of light, the universe's ultimate speed limit, would take hundreds, thousands, even millions of years. Our entire civilization could rise and fall in that time. But what if there was another way? What if you didn't have to travel through all that distance? What if you could just skip it? That's the core concept behind a wormhole. Officially, in the language of theoretical physics, they're often called Einstein-Rosen bridges, a direct consequence of Albert Einstein's general theory of relativity, which teaches us that space and time aren't just a static backdrop, but a dynamic, malleable fabric. Gravity, in this view, isn't a force pulling objects together, but the curvature of space-time itself. Massive objects like planets and stars warp this fabric, creating dips and valleys that we perceive as gravity. Now, imagine that fabric, not as a flat sheet, but as a three-dimensional expanse, constantly being stretched, twisted, and bent by everything in it. If you have 2 points on a piece of paper, the only way to get from one to the other is to travel across the surface. But if you fold that paper, you can bring those 2 distant points right next to each other. And if you could then pierce through the fold, you've just created a shortcut. You haven't moved through the space between them. You've moved around it. You've created a bridge, a tunnel, through the very geometry of the cosmos. That, in essence, is a wormhole, a theoretical tunnel connecting 2 disparate regions of space-time, allowing for what we call superluminal or faster-than-light travel, not by breaking the speed limit, but by bending the road itself. The allure is undeniable, right? Suddenly, the vastness of the universe, the seemingly insurmountable distances, might not be so insurmountable after all. We could reach exoplanets, explore distant nebulae, perhaps even visit other galaxies. The universe, once a distant, unreachable tapestry, becomes a landscape waiting to be traversed. It's the ultimate dream of exploration, the final frontier of cosmic travel. But here's the thing. While general relativity allows for the mathematical possibility of wormholes, it doesn't exactly make them easy to deal with. In fact, it makes them almost maliciously difficult. You see, the wormholes that naturally arise from Einstein's equations are, to put it mildly, deeply uncooperative. The vast majority of theoretical wormholes are incredibly unstable. They would form, and then immediately, catastrophically, collapse. Imagine trying to hold open a tunnel made of pure gravity. Gravity, by its very nature, is attractive. It pulls things together. So, a wormhole, which is essentially an extreme distortion of space-time, would try to pinch itself shut the moment it formed. It's like trying to hold open a doorway in a universe that desperately wants to slam it closed. You'd need something to prop it open, something that defies the very nature of gravity as we understand it. And that something is where we enter truly speculative, almost fantastical territory. Exotic matter. Now, don't confuse exotic matter with dark matter or dark energy. Those are strange enough, but they still have positive mass energy. Exotic matter is something else entirely. We're talking about matter that possesses negative mass or negative energy density. Think about that for a second. Everything we've ever encountered, from the smallest atom to the largest galaxy, exerts a gravitational pull. it attracts. But exotic matter, if it exists, would do the opposite. It would have anti-gravity. It would repels. Instead of bending space-time inwards, it would push it outwards, forcing a wormhole's throat open, keeping it stable long enough for something, or someone, to pass through. It's like needing a giant cosmic spring to brace the wormhole open against the crushing force of its own gravity. The problem? We have absolutely no evidence that exotic matter in the quantities needed to stabilize a macroscopic wormhole actually exists. Our best theoretical models suggest that such matter would violate some fundamental principles of physics, like the weak energy condition, which basically states that energy density should always be positive. If you could create a region of negative energy density, you could do all sorts of crazy things, like create a perpetual motion machine, or even warp space-time in ways that would make Hollywood blush. Now, on the tiniest, most infinitesimal scales, at the quantum level, physicists do speculate about something called quantum foam. Imagine space-time isn't smooth, but a churning, bubbling mess of virtual particles and fields constantly popping in and out of existence. In this quantum foam, it's possible that tiny, fleeting wormholes do exist, constantly forming and collapsing, too small and unstable to ever be useful for travel. We're talking about scales far smaller than an atom, gone in less than a blink of an eye. They're like cosmic bubbles, winking out of existence before you can even register them. But even if we could somehow capture one, somehow inflate it, somehow stabilize it, we'd still be left with another mind-bending problem. Time travel. Yes, that's right. If you can traverse vast distances by bending space-time, you can also potentially bend time itself. A stable, traversable wormhole could theoretically be used as a time machine. How? Well, if one end of the wormhole was kept stationary and the other end was accelerated to nearly the speed of light, then brought back, the effects of time dilation, where time moves slower for the accelerated object, would mean that the accelerated end of the wormhole would be in the past relative to the stationary end. Step through one way, you go forward in time. Step through the other, you go backward. And that, as you might guess, opens up a Pandora's box of paradoxes. The classic grandfather paradox. What if you travel back in time and prevent your grandparents from meeting? Then you would never be born, and thus couldn't travel back in time to prevent them from meeting. A logical loop that breaks causality itself. Most physicists believe that such paradoxes imply that time travel, if possible at all, would be severely restricted, perhaps by a cosmic censorship hypothesis that prevents the formation of naked singularities, or by some self-consistency principle that ensures any timeline remains unbroken. Or, more simply, it just means stable wormholes are impossible. So, where does that leave our interstellar dream? The film, to its credit, grapples with many of these ideas. The wormhole itself is presented as a gift, perhaps from beings who have mastered these physics. And the tesseract sequence, where Cooper finds himself in a higher dimensional construct, is essentially a visual representation of how a hyper-advanced civilization might manipulate space-time to communicate across time. It's a testament to the power of imagination, grounded in the very real, albeit extreme possibilities of theoretical physics. But let's allow ourselves a moment of pure, unadulterated fantasy, shall we? Imagine just for a moment that we do overcome these hurdles, that we discover a stable form of exotic matter, or a clever way to manipulate space-time without it. Imagine humanity builds a spacecraft designed not for speed, but for entering and traversing a wormhole. You'd feel a gentle tug, perhaps a strange disorientation, as the fabric of reality itself reshapes around you. The journey itself wouldn't be a long, boring cruise through empty space. Instead, you'd be inside the wormhole's throat, seeing the universe compressed and stretched in ways that defy normal perception. Light from distant stars, normally separated by countless parsecs, would be squeezed together, creating a breathtaking kaleidoscope of cosmic light. The very fabric of space-time would be your tunnel walls, a shifting, flowing conduit of pure geometry. And then, just as quickly as it began, the journey would end. You'd emerge, not into the familiar starscape of our own Milky Way, but into a sky utterly alien, filled with constellations you've never seen, orbiting a star you don't recognize, in a galaxy millions of light years from home. A new sun would warm your ship's hull. A new vista would unfold before your eyes. Perhaps a blue giant, or a binary system with two suns setting in a fiery embrace. You'd be staring at the impossible, a direct witness to the universe's boundless creativity, transported across unimaginable cosmic distances in mere moments. It's the ultimate dream, isn't it? The ability to step through a door and find yourself on the other side of creation. A chance to truly become an interstellar species, not confined to our pale blue dot, but explorers of the galactic ocean. Today, the wormhole remains firmly in the realm of theoretical physics and science fiction. The challenges are monumental. The need for exotic matter, the inherent instability, the paradoxes of time travel. We don't have the technology, nor the fundamental understanding of physics to even begin to construct such a gateway. But every great journey, every monumental breakthrough, every daring leap of discovery began with a dream. It began with what if? It began with brilliant minds, like Einstein's, pushing the boundaries of what we thought possible. The dream of interstellar travel, of traversing the cosmos with the elegance of space-time itself, is perhaps humanity's grandest aspiration. It reminds us that the universe is not just vast, but also deeply strange and wonderfully complex, and it forces us to ask, if wormholes remain beyond our grasp, what other hidden pathways might the cosmos hold? What other secrets of space-time are waiting to be uncovered just beyond the edge of our current understanding? Because if we can't fold space, perhaps there's another way to outwit the light speed limit, another way to truly reach for the stars. And that, my friends, is a story for another time. We dream of navigating the cosmos, of folding space and time to leap across the vast, echoing canyons between stars. We imagine charting new worlds, planting flags, and seeing sights no human eye has ever beheld. But as we gaze out into that unfathomable expanse, another, even more profound question whispers through the darkness, a question that has haunted philosophers and scientists for generations. If the universe is truly so immense, so ancient, and potentially so traversable, why haven't we heard from anyone else? Where is everybody? This, my friends, is the Fermi paradox. It's not just a scientific riddle. It's an existential punch to the gut. We look up at a sky teeming with hundreds of billions of galaxies, each containing hundreds of billions of stars, and we wonder, statistically, the odds seem to favor life, intelligent life, flourishing out there somewhere. Yet, the silence is deafening. No alien megastructures, no Dyson spheres, no interstellar probes, no cosmic chatter on our radio telescopes. Just quiet. A profound, almost unsettling quiet. To even begin to grapple with this cosmic mystery, we often turn to a brilliant, if highly speculative framework, the Drake equation. Imagine it less as a formula to be solved, and more as a conversation starter, a way to break down the problem into manageable, albeit still mind-boggling pieces. It asks us to consider, how many stars are born each year? How many of those have planets? How many of those planets exist in the so-called Goldilocks zone, where conditions are just right for liquid water? Then, what percentage of those planets actually develop life? And of that life, What fraction evolves into intelligent beings? What percentage of those intelligent beings develop technology capable of interstellar communication? And finally, how long do those civilizations last? Each variable in that equation is a cosmic gamble, a roll of the dice in the grand casino of the universe. And the uncertainties stack up, compounding exponentially. We used to think exoplanets were rare. Now we know they're everywhere. Almost every star in our galaxy likely hosts at least one planet. That's a huge boost to the numbers. But what about the leap from simple chemistry to self-replicating life? That's still the ultimate magic trick of the universe, one we haven't quite figured out how to replicate in a lab. And what about intelligence? Is it an inevitable outcome of evolution or a bizarre, lucky fluke, unique to us? So, how do we even begin to search? Well, for the past few decades, our primary method has been to listen, with giant radio dishes like the iconic Arecibo Observatory. We've scanned the skies, hoping to pick up a signal, a deliberate message, or even just the accidental radio chatter of another civilization's daily life. It's like trying to find a single, specific needle in a haystack the size of a galaxy, while blindfolded and only being able to listen for the sound of that needle dropping. It requires immense patience, dedication, and an almost religious belief that someone somewhere might be broadcasting. But beyond listening for intelligent chatter, we're also actively hunting for biosignatures. Thanks to incredible instruments like the James Webb Space Telescope, we can now peer at the atmospheres of distant exoplanets. We're looking for the chemical fingerprints that might betray the presence of life. Gases like oxygen, methane, carbon dioxide, water vapor, all in concentrations that can't be explained by geology alone. Imagine seeing a planet's atmospheric spectrum and finding a spike of oxygen, just like Earth's. That's a profound moment, a potential aha that could rewrite our textbooks. It wouldn't necessarily be intelligent life, but it would be life. A confirmation that we are not alone in the most fundamental sense. Yet despite our listening posts and our telescopic eyes, the universe remains eerily, stubbornly silent. And that silence is what makes the Fermi paradox so profoundly unsettling. It forces us to confront some truly chilling possibilities. What if we are, in fact, alone? What if life, particularly intelligent, technologically advanced life, is so incredibly rare that Earth is a cosmic anomaly? The implications of that are staggering. It would mean that all the beauty, all the complexity, all the thought, art, and love in the universe resides solely within us, on this fragile blue marble. It would place an immense burden of responsibility on humanity, making our survival not just important for us, but for all of existence. It's a lonely thought, isn't it? To be the only whisper in an otherwise silent cosmos. But there are other, more intriguing, and perhaps even more terrifying explanations for the silence. One of the most famous and most disturbing is the concept of the Great Filter. This idea suggests that at some point in the long evolutionary journey, from primordial soup to spacefaring civilization, there's an incredibly difficult, almost impossible barrier to overcome. And it raises a crucial question. Is the Great Filter in our past or in our future? If the filter is in our past, it means something incredibly improbable had to happen for us to even exist. Perhaps the genesis of life itself is the filter. The jump from non-living matter to self-replicating organisms might be astronomically rare, or maybe the evolution of complex multicellular life is the bottleneck. If so, then we're incredibly lucky, having already passed that hurdle. We're the exceptions that prove the rule. But what if the Great Filter lies ahead of us? That's the truly terrifying thought. It means that most civilizations, once they reach a certain level of technological advancement, inevitably hit a wall they can't overcome. Perhaps it's self-destruction, through nuclear war or irreversible climate change. Maybe it's a novel pathogen, or a runaway artificial intelligence, or a cosmic cataclysm that wipes out all advanced life in a region of space. If this is true, then the very silence we observe is a grim warning, a cosmic graveyard stretching across the galaxies. It suggests that our future, if we're not careful, might be a very short one. Talk about a wow moment that makes you want to crawl under the bed. Of course, there are less apocalyptic explanations. Maybe they're out there, but they're just different. Think about the zoo hypothesis. This suggests that advanced alien civilizations are aware of us, but they've collectively decided not to interfere, treating Earth like a protected national park or a cosmic reality TV show. We're an experiment, a primitive culture they're observing, waiting for us to reach a certain level of maturity before making contact. It's a bit humbling, but it makes a strange kind of sense, doesn't it? If you encountered a species just figuring out fire, would you immediately hand them an iPhone? Or perhaps their communication methods are simply beyond our comprehension. We're listening for radio waves. But what if they communicate through neutrinos, or gravitational waves, or even by manipulating space-time itself? What if their consciousness exists in a way we can't even perceive, like a vast interconnected digital network spanning light years, or beings of pure energy that have transcended physical form? Our current search might be akin to an ant trying to understand human conversation by listening for vibrations in the dirt. We're limited by our own biology, our own technology, and our own very human assumptions about what life and intelligence should look and sound like. And what about the possibility that advanced civilizations simply don't last very long? Maybe they burn bright, exhaust their resources, and then fade away, leaving behind no trace. The universe is incredibly old, 13.8 billion years. Even if civilizations arise frequently, their windows of technological visibility might be fleeting blips in cosmic time. We could just be missing each other, like ships passing in the night, separated by millions of years. The Fermi paradox, then, isn't just about finding aliens. It's about finding ourselves. It forces us to examine our own fragility, our own potential, and our place in the grand cosmic drama. Are we pioneers destined to spread life across the stars? Or are we a fleeting spark, destined to burn out in the quiet solitude of our home world? The search for extraterrestrial life, whether it's simple microbes or hyper-advanced civilizations, is one of humanity's most profound endeavors. It's a journey that pushes the boundaries of our science, our technology, and our very definition of what life can be. It's a quest driven by an innate longing for connection, a deep-seated curiosity about whether we are truly unique or just one voice in a magnificent cosmic choir. We continue to listen. We continue to look. And with every new discovery, every exoplanet, every strange signal that turns out to be natural, the mystery deepens and our sense of wonder only grows. Because whether the universe is teeming with life or whether we are the sole custodians of consciousness, the implications are equally profound. The answer, whatever it may be, will redefine everything we thought we knew about our existence. And what if the most incredible discoveries aren't about finding them out there, but about finding something truly extraordinary within ourselves? What if the greatest journey isn't across the stars, but into the very nature of what makes us us? The universe, it's a tapestry woven with light and shadow, with creation and eventual demise. We've explored its vastness, delved into its mysteries, and pondered our fleeting place within its cosmic dance. But what about the end of the dance itself? What about the universe's ultimate destiny? It's a question that humbles and inspires us in equal measure. a profound inquiry woven into the very fabric of our scientific curiosity. Imagine a future so impossibly distant, so utterly beyond our comprehension, that stars themselves have flickered out, leaving only a cold, dark void. This is one of the most compelling and perhaps bleakest predictions for the universe's ultimate fate. The Big Freeze, or as scientists call it, heat death. Picture a cosmos where every star, from the smallest red dwarf to the most colossal blue giant, has exhausted its nuclear fuel. Its final embers, long extinguished. Every black hole, even the supermassive titans at galactic centers, has slowly evaporated over unimaginable eons through Hawking radiation, leaving behind only the faintest echo of their existence. The last photons of light, stretched thin by an ever-accelerating expansion, have faded into oblivion. The universe would expand forever, growing ever colder, ever emptier, until even the concept of temperature loses meaning. It would be a vast, silent graveyard, where the last remnants of matter are so far apart, so incredibly diffuse, that nothing could ever interact again. No energy, no warmth, no light, just an infinite, frigid expanse. A whisper of what once was, echoing into an eternal night. But what if gravity, that invisible hand that sculpted galaxies and birthed stars, isn't the only force at play? Or at least, not the dominant one in the far, far future? What if the universe's expansion isn't just accelerating, but accelerating so violently that it literally tears everything apart? This brings us to the Big Rip. Envision a cosmos where the mysterious dark energy, that enigmatic force driving this acceleration, grows so incredibly strong that it begins to rip apart galaxies, then star systems, then planets, then mountains, then atoms themselves. Imagine the very fabric of space-time being shredded, literally pulling everything, every particle, every fundamental force, into individual isolated fragments. It's a terrifying vision, a cosmic cataclysm, where the universe doesn't just fade away, it's violently unmade, disintegrated from the inside out, a final, agonizing scream across the void as the very bonds of reality unravel. And then there's the third, more cyclical possibility, one that holds a strange allure, the Big Crunch. This scenario, once a favored theory, suggests that if there's enough matter and energy in the universe, gravity would eventually overcome the dark energy's expansive push. The universe, having ballooned outwards for billions of years, would then begin to contract, slowly at first, then faster and faster, reversing its grand journey. Galaxies would hurtle towards each other, stars would collide in fiery spectacles, and eventually all matter, all energy, all of space-time itself, would be crushed back into an infinitesimally small, unimaginably dense singularity, a reverse Big Bang, perhaps setting the stage for another cosmic rebirth. A universe that breathes in, then breathes out, in an endless rhythmic dance of creation and destruction, a cosmic heartbeat echoing through eternity. We don't know which of these fates awaits us. Our current measurements of dark energy suggest the Big Freeze is the most likely outcome, a slow, quiet fade into eternity. But the universe has a knack for surprising us, for revealing layers of complexity we couldn't possibly imagine. And while these ultimate destinies feel impossibly distant, unimaginably grand, they cast a long, profound shadow over our present. They compel us, these cosmic inevitabilities, to look beyond our pale blue dot, to dream of futures we might never see, but futures we might, in some small way, help shape. They demand that we ask, what will we do with the time we have? Because confronted with such overwhelming existential questions, what is humanity's response? Do we simply resign ourselves to the cosmic clock? Do we give in to the chilling inevitability? No. That's not who we are. Our entire history, our very evolution, is a testament to an unyielding, insatiable drive to explore, to understand, to overcome. We are the species that looks up at the stars and doesn't just see pinpricks of light, but an invitation, a challenge, a profound mystery waiting to be unraveled. And when faced with the ultimate boundaries of space and time, the unimaginable distances between galaxies, we dream of finding a shortcut. We dream of the wormhole. Remember the dream of Interstellar, that cinematic journey through a cosmic tunnel, a shortcut flung across impossible distances, linking worlds separated by unimaginable light years? It wasn't just a fantasy on screen. It was an echo of a deeply human yearning. The wormhole, this theoretical Einstein-Rosen bridge, is more than a scientific concept. It's a powerful symbol. It represents our audacious hope to transcend the limits of the known universe, to bypass the tyranny of cosmic distances, to cheat the light speed limit and leap across the void. It's the ultimate expression of our longing to connect, to discover, to escape, if need be, to ensure humanity's survival, humanity's future. It is the perfect metaphor for our refusal to accept limits. Of course, the science behind a stable, traversable wormhole is mind-bogglingly complex. We'd need something utterly bizarre, something called exotic matter, matter with negative mass or negative energy density, to prop open such a cosmic doorway. It's material that defies our everyday experience, a theoretical construct that might exist only in the most speculative corners of physics, a concept that stretches the very limits of our current understanding. It's like trying to hold open a collapsing tunnel with invisible, impossible hands, with forces we can barely conceive. Yet, that's the beauty of the dream. Even if the physics remains elusive today, the idea of it fuels our imagination, pushes the boundaries of our understanding, and reminds us that what seems impossible today might just be waiting for a new discovery, a paradigm shift, a flash of human genius to unlock tomorrow. The greatest breakthroughs often begin with what sounds like pure fantasy. The interstellar dream isn't just about finding a new home amongst the stars. It's about the journey of discovery itself. It's about the incredible effort, the brilliant minds working tirelessly in labs, the sheer audacity required to even imagine such a feat. It's about the emotional toll, the hopes and fears of those who dare to push boundaries, the countless failures endured before a single triumph. It's about characters like Cooper and Brand, making impossible choices, sacrificing everything, not just for their own survival, but for the survival of their entire species. That's us. That's humanity. We are the inheritors of a cosmic legacy, a universe that birthed us, nurtured us, and now challenges us to look beyond, to grow, to evolve. We are, in a profound sense, the universe's way of knowing itself. We are the consciousness that perceives the big freeze, the big rip, the big crunch. We are the minds that grapple with dark energy and dark matter. We are the hands that build telescopes to peer into the cosmic dawn, and probes to touch other worlds. And with that unique, improbable position comes an immense responsibility. A responsibility to cherish this fragile consciousness, to nurture it, to expand it, and to ensure its survival, not just on this planet, but perhaps one day, across the stars, carrying the flame of awareness into the cosmic night. Our future here isn't predetermined by the cold mechanics of cosmic expansion or contraction. Our future here is written in our choices, in our collective will, in our unwavering commitment to exploration. The dream of the wormhole, of faster-than-light travel, of interstellar migration, isn't a desperate escape from an inevitable end, an affirmation of our ingenuity, our resilience, our unyielding belief that there is always more to learn, more to see, more to become. It's a testament to the fact that our greatest strength isn't muscle or might, but the infinite expanse of our imagination. So let us continue to dream, Let us continue to build. Let us continue to explore both the universe outside us and the boundless potential within. Whether we ever step through a real wormhole, whether we ever reach another galaxy, the act of striving, the pursuit of the impossible, is what defines us. It's what elevates us. It's what makes us worthy of the vast, intricate, and astonishing universe we inhabit. We are here, on this tiny speck of blue, poised on the edge of an infinite horizon. The cosmos beckons, not with definitive answers, but with an enduring invitation to wonder, to look up, to question, to innovate, to protect, to create, to embrace our role as stewards of consciousness in an evolving universe. This is our cosmic destiny, not to merely witness the end, but to write our own beginning again and again in the endless story of time and space. The greatest journey truly is within us, within our capacity to dream, to connect, to be. And that journey for humanity has only just begun. It's a journey fueled by hope, guided by science, and illuminated by the unquenchable, magnificent fire of the human spirit. And it is glorious,